Is it streaming or not? Yes, sir. Yes. Yeah.
I think it was the first thesis of radio measurements from India, and that was during 1990 to 96. And later on, he went to Boston University, worked for 10 years, and he initiated the data in aeronomy. So that's a very important in Boston University, and he built new instruments for that. And he's an expert in space weather studies. Uh, he has guided several PhDs, 5 PhDs, 8 postdocs, and he is one of the fellows who work both in the Arctic and Antarctic, even up to the Greenland. He has also worked in Greenland making measurements. And recently he was elected fellow of the Indian Academy of Science. He has many laurels to his credit. Without taking much time, I invite Professor Pallamraju to give his talk on space weather science. You want to say something?
Sir, I'll get up there.
Yeah.
Thank you, sir. Welcome, audience, for the 44th Ananthakrishnan Colloquium. So I will read out the credentials and introduce the speaker today. It's a great honor. So Professor B. Pallamraju did his MSc in Physics from Osmania University, Hyderabad in 1990 and PhD from PRL in 1996. So after a year of stint as postdoctoral fellow at PRL, he worked at the Center for Space Physics in Boston University, Boston, and as a senior research associate over 10 years. At present, he is working as a senior professor at the PRL and holds the position of dean at PRL. So, scientific interests of Professor Pallamraju includes the space weather effects on geospace, vertical coupling of the atmosphere, upper atmospheric wave dynamics, plasma-neutral interaction during geomagnetic storms, and excavation of new methods of investigations of the upper atmospheric dynamics. He has the rare distinction of carrying out daytime auroral experiments from both Antarctica as part of the 13th Indian expedition to Antarctica in 1993 to 94, and Antarctica and Greenland for the investigation of space weather effects on the Earth's upper atmosphere. So he has supervised the 5 PhD students and 8 PDFs over and published over 17 peer-reviewed publications to his credit. And Professor Raju had served as the elected secretary of the Solar Terrestrial section of AOGS in 2011 and 2015, and coordinator of the climate and weather of the Sun-Earth system in 2004 to 8, which is an international program of scientific commission on solar terrestrial physics. And science discipline representative and many more are to read actually. So with this short introduction, I welcome Dr. Pallamraju to give his colloquium. Thank you.
Okay. Good afternoon. Thank you, Professor Ananthakrishnan, my alma mater at PRL, for the kind invitation and for the nice introduction. It's a pleasure to meet senior colleagues and also to learn about the strides that IITM has been making. And when this discussion came about, they said that when you people are looking at the weather on Earth, and there is another weather in the space, so I thought that this could be an opportunity to look at or to just introduce you to this domain of contemporary research. It's going to be one of the most frontier areas of research as the time goes by in this in the next decade to come. And it's again an honor to be associated with the IITM Professor R Ananthakrishnan Colloquium series. And the topic that, as I shown here, it is space weather science and its effects on societal applications. And what this represents is the sun, and this is the earth on the right side. So the space weather is between these two. And this is the logo of PRL. And just to give a brief of that, that left, on the side you have a dot and the circle that represents the sun. And on the right, you have the plus mark in the circle, which represents the earth. And what you see here is the kind of magnetic fields. We are engulfed in the interplay, the magnetic fields of the sun and the earth, and there is, and then it's again, it goes beyond sun and the earth. And the kind of research topics that we have are in astronomy, astrophysics, solar physics. Here you can see space and atmospheric sciences, atomic, molecular, and optical physics. And then we have planetary sciences, geosciences, theoretical physics, and we have a strong student and postdoctoral fellowship program. And at PRL, just I wanted to say that we have 4 campuses. This is the main campus in Thalpej, Udaipur Solar Observatory in Udaipur in Rajasthan. Mount Abu also is in Rajasthan. And we are just now, we completed our 75 years of formation. To Dr. Vikram Sarabhai's vision, PRL was formed immediately after Indian independence on November 11, 1947. And we had this Platinum Jubilee celebrations. And among that, we had several top programs that we have initiated. One is what is called the 75 years, PRL Ka Amrit Vyakyan, wherein we had taken, imposed upon us that we'll have one colloquium every week uninterruptedly. So 2001, this colloquium series started. We have 75 of them, which finished earlier this month, this year, January 5th. And I'm happy to say that, Dr. R. Krishnan, Director IITM, is also one of the Vakta, or he gave one of the colloquium in this Vyakyan series. And I think this is the link of PRL YouTube webinar. So you can see not only his, his colloquium, but several others given by several diverse areas of experts, right from, in sciences, engineering, arts, law, medicine, and so on. So after the brief introduction of PRL, let me come to this today's talk. And before I go into the talk and other details, I would like to acknowledge the sources that I have used, because this is a big international level program and science. And I happen to be to have had played a role in various international programs of CAUSES, Presto, and Varsity. These are all the Scientific Committee on Solar Terrestrial Physics COSTEP programs. COSTEP itself is a international science union body, and we have several programs coming out every 4 or 5 years. Again, NASA, NSF, and ISRO resources, several interactions with several scientific colleagues, publications, books, and some ground-based radar maps and some information on refereed publications. So with that, a disclaimer, and I would like to go from known to unknown. We all know what do we mean by the weather, and we mean, how do you measure weather? Okay, you say then it is you have some of the parameters, temperature, wind, humidities, wind velocities, directions, and so on and so forth. And we have methods in which you can see the map, through Kalpana satellite. You can see the map on the ground, and you can see the cloud coverage, and if there is a cyclone that is getting formed. Obviously, with the time of, I don't need to tell this audience here, but we know that we can get the directions and predict exactly when it's going to hit a course and a coast. And obviously, if now that thanks to all the nice predictions, there is no human losses, but then these disturbances in the weather leads to, several losses, both in terms of precious resources. So this we are aware. Now with this understanding, if you look at what is space weather is by definition refers to the conditions on the sun and in the solar wind, magnetosphere, ionosphere, and thermosphere that can influence the performance and reliability of spaceborne and ground-based technological systems, and that endanger human life and health. Adverse conditions in the space environment can cause disruption of satellite operations, communications, navigation, and electric power grids, leading to several socio-economic losses. So we are in this era of looking at space and how the space, the sun itself, as you see here left, the sun itself has a 27-day rotation. And as it rotates, there are features on the sun. They also rotate with the sun. And you can see on the right is the Earth, wherein you have seen, what you see the circle is an aurora, borealis in the northern hemisphere. And then there's a brightening of light, which is because of the auroral emissions, which indicate that there is a storm, solar storm, that has come and hit the Earth's upper atmosphere, ionosphere. This happens at 100 kilometers and above. So that's where our satellites are orbiting. Okay. So as far as the pure fundamental science is concerned, there is the sun-Earth system. Can be shown in this one slide, wherein you have the sun here with several dark spots, which are the sunspots. You have what are called the coronal mass ejections, with huge amounts of mass in terms of around several tons, 10 raised to 9 tons of mass in electrons and protons, get mainly protons, get ejected from the sun, and then they move towards the Earth, and there are a lot of shocks that are produced in between. And then you have here Earth's magnetosphere compressed because of solar wind. You have this, it's a bow-shaped structure you can see here. And inside you have all these features, magnetosphere, plasmaspheres, and various other spheres that we live in. So we're looking at what is happening in the geospace. So geospace is I define it as the space which until the geostationary satellites orbits, so that we know that it's 36,000 kilometers, and this is we are interested because we live in it, and almost all the orbiting satellites are in this region, which does get affected because of the effects between the sun and the Earth, and what is called the space weather is formed. So that's why this is the domain that I'm restricting myself to. So if you say, are the space weather effects dangerous or harmful? Probably, like lightning might kill you, but not space weather, will not kill you. But it affects all the several satellites which are in the direction of the sun and Earth, and all kinds of satellites with our navigation, communications, and all our other applications that we have, including the satellite that is used to measure space weather, and every satellite gets affected. And obviously it deteriorates GPS signals because atmospheric densities change, and then again because this and it can change the neutral density is and then drags are introduced on the satellites. It can damage transformers and can take down hydro electric powers network in pretty quickly. and it induces currents in the corroded oil pipes and lead to explosions, and increases the satellite drag, thereby shortening their lifetime. So in that sense, the space weather is of importance to study and understand, at least to be aware of that this is the thing. We are living in a nice cocoon here, but a lot of things are happening beyond, which is making our life possible here. And from the fundamental science point of view, there are various factors that are coming in: the sun, the interplanetary medium, the various spheres, magnetosphere, plasmasphere, ionosphere, and thermosphere. And at least, these are just, I'm just putting down some of these phrases, not going into details of that, but these are all the elements. I'll just touch upon each of them in a slide or so as I pass by. Our sun, of course, has over 99% of the mass of solar system, and it's mostly gas, and it burns several tons of mass each second. It's a middle-aged star, and this emits enormous fluxes of energies which vary over a large magnitude and also into large time scales, from few seconds to decades. And just to get a comparison, it's 100 times that of the Earth size. So we are just a blip in the whole scheme of things. So we can't do anything if sun, behaves in a different fashion. But we need to understand how can we protect ourselves when this kind of things happen. And this is the various regions of the sun: photosphere, chromosphere, and corona. And what we see from, if you have a filter and look at the sun, what you see is a photosphere, and it will the topmost layer, and it emits in the visible region. As you go into the chromosphere, higher layer, it emits in the ultraviolet region. It is 10,000 K, temperature increases. And you go to the corona, it is X-rays, it emits X-rays, and you can see it's a 1,000,000 degree temperature. And you can see that corona only during the eclipses. Okay, the photosphere is something like this. It looks like black dots, which are nothing but the magnetic fluxes coming out. These are and then this number of spots keep increasing with the solar cycle. Sun, as I said, as you may be aware, it has an 11-year cycle and a 22-year magnetic cycle. So this is during a high solar activity. You can see several actually there are a lot of sunspots here, and then this is a picture taken out in the ultraviolet. So you can see that there are so many UV emissions taking place. This is obviously, as I said, these emissions are from chromosphere, higher layer, and then you can see that active sun, it can be like this, and the quiet sun can be like this, small 1 or 2 spots, and here there are more and more sunspots. And when you say corona, as I said, it can be seen only during eclipses because the solar disk is pretty bright. So the disk has to be covered. So that happens perfectly during lunar eclipses, and then again there are annular eclipses and all. So let us consider the total solar eclipse when exactly the whole diameter of the sun is eclipsed by that of moon, and that's where you will see this corona. And this, but to observe this corona, we have put what are called the coronagraphs over Lagrange point, L1 point, which is 1.5 million kilometers away from the Earth. There, if you just do the calculation, the solar gravity and Earth's gravity both match, and then you have a point wherein you can look at the sun continuously. So, and there you put what is called the corona graph here. This is a circle, is the diameter of the sun. So you block a little bit more so that you can see what is happening in the corona. So what you are seeing here in this is a coronal mass ejection, and then here you can see the huge things are coming out, and then that has come and hit the detector. Actually, that's why you see all this bright, the scratches kind of thing on the detector. Okay, and then so this can around, as I said, can eject 10⁹ tons of mass. So E is equal to mg squared. That's how the whole energy is lost. The mass is getting lost, energy of sun is getting lost. And then next we come to the interplanetary magnetic field. Its origin is the sun, and then it goes radially away. And then as the sun, and again, as the students of physics, we know we can make that into components of Bx, By, and Bz. And the important thing is that of BZ, has to be, southward for the effect of these high energy particles entering into the Earth's atmosphere. And that is shown in this kind of video. You can see the sun is rotating on its own axis. It takes 27 days. So the magnetic field lines are swept along with it. The closer magnetic field lines are attached to the magnetic field to the sun. So they are moving faster when the other ones are getting dragged there. But then that whole, you can see the arrow there, it is flipping. That is that the BZ, is dancing, X and Y. It's something like a frock wherein they can be unfolds, at the end of the at the radially away. And because of that, it makes the Earth's magnetic field compressed in the day side, because this is the whole thing is pushing. This is how if there had not been any solar wind, magnetic field of the Earth would have looked like. We have all done the iron filings experiment, wherein we can just see in a magnet how these nice field lines we can see. This would have been the case, but that is not the case. In the real scenario, this is like this, and then the day side is compressed, and then the night side is elongated. It can go very far away, until 200 Earth radii also. The daytime, it's around 10 to 12 Earth radii. Earth radius is 6,300 kilometers, as you know. So day side is compressed, night side is far away. And what happens is that, I was telling you, BZ has to be south in the sun. That's what the red line here represents, the BZ south. Okay, when the BZ is south, then that combines with the Earth's magnetic field. This is rejoining.
Please rejoin and open the page.
It says that it has one of the but my PowerPoint is closed. That's what I got a message.
Yeah.
So I just I'll do so.
Sharing. Yeah,
that is opening up. That's what is opening up.
Yeah, we are opening. Right. Yes, wait, we are opening. You hear us, right? You hearing us, right?
Yes. Because I'm sharing the screen.
Share the screen already shared.
Oh, that's right. That's right. Okay, it's open.
Just a second. Can you repeat?
Microsoft Teams.
Please close the Firefox tab.
Yeah, Microsoft. Yeah, so yeah,
Do you have any Firefox open?
Yeah,
Close it.
this one is opening up.
Just wait. I think it's heavy fire. Are you seeing the screen? Okay. Are you seeing the PPT? Go to the slide viewer.
Yes.
Okay.
Yes. Yeah, sorry about that. So what I was saying was the red one here is the magnetic field line that is southward. Earth's magnetic field lines are always northward. So there is a mix. There is a what is called magnetic reconnection. Once that happens, there is an opening up of the gateway, so to say, and the particles can enter into the Earth's upper atmosphere. And then this happens both in the day side and night side. And what you are seeing here is a particle entry into the higher altitudes, so the cusps regions. And then what you are seeing here is particles coming into the magnetic cusp region from the high latitudes there, and then I think I should close this one because it is opening in multiple. I think I now closed that. I noted that.
Yeah, please close down the file.
Yeah, I closed that. I think that one was taking out some of memory. Yes, sorry about that again. So this is how the particles are entering into the Earth's cusp regions. That's where the gateway is what is generated. And if we kind of summarize what all is happening, what all I discussed so far in a movie, right in what you're seeing, looking at the sun, and then you have an active region there in the white spot there. There is a coronal mass ejection that has just erupted, and that eruption is now coming towards the Earth. There's a lot of acceleration happening in that region, and then that hits the magnetic field here, as you are seeing. And then once the magnetic fields are hit, then they're opening up here, as you can see, magnetic field lines. And then the particles entry into the upper atmosphere there, and then there's a reconnection again, as I said, in the night side. And then there's a particle acceleration because of it's something like open rubber band. It is released. Then huge amount of particles, large energies come in, and what is formed is aurora. So this is all the process that has happened from sun to the earth into the ionosphere thermosphere. Ionosphere thermosphere is this region where, as I said, that's all the satellites are orbiting, and that's the the sun is the source of all the energies that release, and the ionosphere thermosphere is a region which receives all these energies, and all the disturbances happen in this ionosphere thermosphere. So that's what that's the core area of the space weather effects that we are looking at. So so this is as we all know, sun has a 12 years of 11 years of cycle, and then the sun is in solar maxima. The Earth's thermospheric temperature can increase up to 2000 Kelvin as well, while at minima it can be around 1000 Kelvin. So that whole upper atmosphere expands and contracts in an 11-year cycle. And then once the larger radiation, because solar maxima, there's more extreme ultraviolet rays and UV rays and X-rays are emitted, which are order of magnitude larger. And visibly, there is the visible spectrum, there is not any change. That's why we don't see 11-year cycle from our naked eye. When you look at the particular light in the sky. But then in the extreme ultraviolet and UV regions, there is huge variation. And the Earth's upper atmospheric species, what are they? There are O2, N2, O, and these are all the species that are there, which get ionized. So ion densities increase and decrease as solar maxima, solar activity increases and decreases. And these events, when this kind of huge things are hitting the Earth's upper atmosphere, is called the space weather. And as I said, that's space weather effects on geospace. That's what it concerns us. And one of the beautiful manifestation of that is aurora, as seen from ground. From ground, you're looking at up by, see the green color. Again, there's a lot of physics in it. The green color comes because of atomic oxygen emission, green line emission, 5577 nanometers. So people have traditionally made, looked at this kind of visible light and made some scientific studies of what is the energies of particles that are coming in. These are high energy particles coming in until 100 kilometers. And another thing that you are seeing here is from a fast satellite. You can see the green in the bottom, some white here and red here. Okay, so red is coming from the top, which is low energy due to low energy particles, low energy requirement. But then you see the white there. Obviously that means that this is a combination of all the RGB. That's why you see white color. So there are a lot of colors there. Every color represents a particular atomic or molecular transition. So that's what the study of air glow or aurora, leads to. That's what my specialty is, that we do this kind of experiments. It's kind of passive remote sensing. This is, if you want to know what is air glow or aurora, it's basically nothing but an initial source of excitation is solar photons. It's called air glow. While if it is energetic particles, as I showed you in high latitudes, that's called aurora. And that is, these are just the atoms or molecules here represent X and XY, and so on and so forth. Now they are in X. The star I have put in red color. That means that they are in excited state because of the energies received from this kind of either photoelectrons or photons or whatever be the source. And once these excited species come down to the ground state, to conserve energy, they give out photons. This can be from far ultraviolet to infrared. The whole gamut of visible spectrum can be emitted, and that's what is called the air glow. And this spectrum, this photograph we have seen earlier, and this is the whole aurora, and it's a big, you can see the whole auroral oval compression and expansion. This indicates, now that you know what is magnetic fields are doing, you can imagine magnetic field line there, traversing up and down, on the top of the Earth actually. And that again tells about, this is a very severe geomagnetic storm there that is happening. That's when this happens, we call it geomagnetic storm. Just like our cyclones and hurricanes here in the ground, we call them, these are called the geomagnetic storms. I don't know what's happening. Maybe what I'll do here is put it like this.
Yeah, I think that's better.
Yeah.
Yeah, that's good.
Okay. Yeah, and therefore you can see sometimes it was all traditionally there's a lot of red here. Red is nothing but oxygen red line emission, and people in in Greenlandic region, tribes and all, they have recorded this kind of things that are happening over hundreds of years. And this red, they thought it's a bad omen, because in Europe a lot of wars used to happen very often, so they thought that this is a bad omen. Anyway, but this is not only high latitudes, but what I wanted to say is that low latitudes also this have an effect on space weather. This is what is shown here is our own relative kind of instability that has happened, range, time, intensity maps on this from the Indian MST radar at Gardanki. And you can see with the time, you can see the echoes. The radar beam is sent and you get receive a return echoes, and they correspond to certain scale size. Here in terms, in this is 3-meter scale size irregularities. So when this happens, Ionosphere, because of these irregularities, the communication signal is lost, and these are represented by optical measurements by airflow images. They look like plasma bubbles, and these are elongated along the magnetic field lines. So there are various ways to look at this effect. But what I'm trying to say is that these space weather effects are in low effect, do affect low latitudes also. In fact, low latitudes, even irrespective of geomagnetic storm, there can be plasma irregularity formation. That's another area of research. But then that also has an effect on the communication. Finally, the result is our communications get affected. And these are again another maps with the same range, time, intensity. It can go up to very 560 kilometers. And so I'll now talk about the adverse applications. So far what we have seen is the space weather. What is space weather in terms of the science and what is happening until the Earth's upper atmosphere. But there is a lot of adverse effects, which are something called the single event upset events. Okay, SEU. These are where the magnetic, satellite, all the satellites, find there are a lot of anomalies have been reported. Something like a bit errors in the satellites, the electronics, or they have not sent a signal properly. And when they have looked at these anomalies are larger over the South Atlantic anomaly regions. And these are again because of the magnetic field line configuration geomagnetically and different locations. The magnetic field intensity is larger, as we know. So this makes the particles to enter there and then create anomalies. And then when the geometric storms are happening, this kind of anomaly does have another show larger particle incidences. So this is one of the direct effect of space weather. Another thing is in terms of on the spacecrafts. They are orbiting. What we have in the upper atmosphere is ionosphere. In the ionosphere and thermosphere region, what we have is electrons or ions. And then because I told you that it's something like a rubber band, when the magnetic field line is stretched in the night side, and as it is released, particles are energized. So there are relativistic electrons. They come with a very large energy. So there can be three kind of effects. Ion hitting the satellite. So that's what is shown here. This ion affects, what happens is that these ions have mass, massive, so they can form tracks on the solar panels. So after some time, there can be disruptions in the functioning of the solar panels, or the electronics and the communication to the satellite bus itself. So that's how they can affect. And then when that kind of things happen, you can see a huge, and this is a July 2000 event, wherein at 7 UT, you see that there is an extreme UV image taken from the L1 point, Lagrange point, as I told you. You can look at the sun all the time. And then these are UV, the photons, they're coming in 8 minutes time, you can see it. See them on the detector. And immediately you can see by 1328 UT, the particles have really come and hit. So they have traveled at a huge speeds, more than 1,000 kilometers per second, more than that, 2,000 kilometers per second speed they have traveled. So that kind of things can happen, and several things would have hit the solar panels and satellite body, which will have, and that's why every satellite has got a lifetime, because they have to take into account all these effects. The other effect, as I told you, it's a relativistic electrons. So the relativistic electrons will have energy to pierce through your satellite body, and they can come in actually. And then once they come in, it is something like, how can they come in is because of this is the nighttime thing, as I showed you. The particles in night side here, when they get recombined, you get particles energized, and then you have huge energies coming into the system. And it's something like, once this kind of energies are there, the particles can go through the satellite body, go into the satellite coaxial cables, and get deposited. And then if the rate of deposition is greater than the rate of leakage, what happens? It's a conducting layer it forms, and it's a kind of electrostatic discharge. The audience here knows what the discharge is. It's something like a lightning. Okay, so this is kind of things can happen, and in the satellite electronics. And this is a ESD image wherein the kind of simulations and experiments have been done. You can see that CMOS chip, the dot there, and you can see the blown up region. This kind of things have happened on the CMOS chip. So if that kind of thing happens in the space, whatever this CMOS chip is supposed to do, the functions, they are interrupted and they are lost. And then the other is the low energy, the electrons which don't have enough energy to go into the system, but they go and get charged, go and get deposited on the body, satellite body. When satellite bodies, more and more electrons are deposited, it becomes more and more negative. So all the satellite electronics, they have a reference with the satellite body. So the bias voltage changes. So your satellite electronics can again have a have malfunction. So these are all things that happen during space weather. This is just only a sample I have shown you, but there are several things that happen. And then there are several satellite observatories in the sun and Earth region actually. And all these things do get affected, but they are to be sent also to study the phenomena. So there are a lot of experiments and observations are going on, and there are a lot of civilian spacecraft, the geostationary orbit that are Kalpana kind of satellites. Every country will like to have few of them to further cater to their own citizens' needs. There are several, and of that, so all these do get affected. And once the now we're coming to the other things, satellite operations, we can see that in the how do we, so because as I told you in the beginning, we can't really stop things from happening, but we can prevent things from damaging our systems. So what do we do? When the signals are there, you can turn off for your instrument so that it is not disturbed, not damaged more. The maneuver can be changed, rather than being in the line of sight, you can go away. And again, orbit determination accuracy change is varied, gets affected. And I think one of the example of things that you have heard in the recent times is the 4th February. The SpaceX satellites got burnt out. With the Starlink thing, all 49 satellites were lost because of the geomagnetic storm, because the orbit geomagnetic storm induced effects which induced the satellite drag, and then these satellites were brought down, and then they couldn't overcome the gravity, and then they eventually landed or burnt out as they come to the Earth's atmosphere. And these kind of things, electric power grids, this is the actual picture of the transformer getting burnt because of the currents that are generated in the high latitudes, because there are ionospheric currents that are from auroral. Oval means there is a lot of current there. A lot of particles are moving around the current. Once there is a current, there is an induced current on the ground, on the electric grids. So this current, we know, Joule heating, J equal to I square R. So current increases, then by square of it, the heat increaes. And this is a burnt, satellite, burnt transformer. This is a picture taken from Canada. And you have other effects that are happening are the space travel, actually. So when you have polar, flights now going more and more from across the high latitudes, if you have a Delhi to, now US flights, there are several going which go along the pole. One is the communication gets affected exactly when you're what is called the polar cap. So they have to depend on different, frequencies. And also a study of, storms was done, wherein the kind of radiation that doses that the flight attendants and the pilots they are exposed to is significant, over a period of time, actually. So that gets affected. GPS systems get affected because you're using the GPS for oil and natural gas and water, surveying and all. And as I said, these, because ionospheric irregularities, the positioning affects changes, so the kind of accuracy of drilling and the locations, they are affected. And obviously, whereas various currents get generated, and these enhanced currents corrode the pipelines. So that has an effect on the ground systems. The effects of, again, humans in space activity, human, now that we are having Gaganyaan and other countries have sent people to move on the space. So these people do get affected because of the various radiation doses that are radiation they're exposed to, and the various studies in which how can the thing in degeneration of tissues, respiratory diseases, damaged central nervous system. Several of these things can happen if the radiation is larger. And then, so in one of the storms in October 2003, astronauts aboard the International Space Station experienced increased radiation levels and had to stay inside, more shielded, locations. And in India also, we are in terms of Gagan network is there, joint ISRO and Airport Authority of India project to improve the accuracies in terms of ranging of the positioning, ranging and different signals and integrity. All these get affected because of the ionospheric variations. And as I said, low latitudes have any additional effect in addition to the space weather effects. We have our own effects. So this is the summary of the impacts on technological systems. Astronaut safety, as I told you, as atmospheric drag, that changes, and then airline passengers, they're exposed to radiation, and they can't, again, it becomes it's a multidisciplinary problem because it's an economic and economic problem also. If you go in higher altitudes, you're getting more and more dosage. So you can come down in altitude to reduce the dosage, but because you come down in altitude, drag increases. So the fuel costs are larger for airlines. So it's an optimum. And again, you can't go in whatever altitude you want to go because there are again defined altitudes for every direction, north to south, east to west, and things like that. So you can't. So there's not much of maneuver you can do. So and then, as I told you, because of the plasma bubbles, as I showed you, because that is larger and low and higher and lower densities in plasma bubbles. So they get affected because of the signal that is coming, GPS signal that is coming through that. And then what we are receiving here is signal delays, and then there is corrections need to be made, for which you need to know ionospheric variations accurately, and things like that. And then we have these ionospheric currents, and then there is the return earth currents actually, and the telecommunication cable disruptions. All these things happen when the effect between the sun and the earth is in a different fashion. So this is several other things, because we don't directly come and hit on our bodies. We don't know, and then luckily thanks to the magnetic field lines which are protecting us, that we don't know that these effects. Magnetic field lines would not have been there. There would not have been any life on any planet. Then the whole because of solar wind itself, they would have dragged away the whole atmosphere away. So because of magnetic field lines, there is life on Earth, and that's why we don't see it on the ground independently, but we see it through societal applications, because all these applications depend on the ionosphere behavior, and because and that gets affected because of the solar storms. So basically, the question is, can we predict space weather events and geo effects? And that's exactly one of the frontier research areas around the world. And at PRL, we carry out research with an aim to scientifically understand various mechanisms through which transfer of energy and momentum takes place, and what are their effects on our latitudes. We use optical, as I was mentioning, radio probing and simulation experiments to understand the science that creates these disturbances. And we carry out experiments from ground-based platforms. We fly instruments for rockets, and we have experiments on satellites planned for various for this kind of space weather studies. One of this is one of the mission which is in pipeline planning from ISRO. It's called the Dual Aeronomy Satellite Mission (DISHA), Disturbed and Quiet Time Ionosphere Thermal System at high altitudes, wherein we are looking at two satellites going in one high inclination, one in low inclination, collecting all the basic parameters that are required that describe the ionosphere and thermosphere in various times of the day, various latitudes, various longitudes as a function of time. That is in the solar cycle, So it's a planet to be having a 5-year kind of mission with a kind of few years of overlap between the DISHA H and L. So we are. So this is something like having our own monitors. In the societies, we have all the cameras now, just to know who is coming in, who is going out, just to evaluate or to prevent somebody from unknown from coming in. In the same way, these will be our eyes in the sky, in the space, and these are some of the configuration in terms of we are flying in. This is, of course, several institutes are involved, and we are having optical image instruments, electron temperature instruments, electron density instrument, neutral densities, drifts, because ion drifts that are happening, airglow emissions that are coming out, and auroral X-ray emissions. And so just to summarize, I think what I have done is we have very briefly and very broadly reviewed what is space weather science, and also we have seen what are the effects, adverse effects of the space weather disturbances on the satellite and ground applications, which is in the domain of geospace. It is essential to gain a better understanding of these effects in order to assess the consequences or prevent the damage. And it's obvious that for sustainability of humans and systems on the Earth, it is important to understand the space weather. And I have already told you it's a multidisciplinary area of research with scientists, engineers, modelers, policymakers, all have a role to play. And we had a lot of meetings in the last year wherein several ministries have come in and they showed interest in joining this in various ways in terms of either modeling or in terms of usage of various aspects of these kind of space missions. And as I conclude, I would like to say that several intricacies of this frontier area of research are yet to be understood. It's an exciting time to be carrying out research in this area of space weather, and you're all welcome to join in whatever way you can, and at least be aware of there is space weather rather than this weather as well, which is making our day-to-day life, all our mobiles, phones, televisions, everything is working. If space weather disturbances are there, all these things will go down actually in no time. And we are getting more and more affected now because we are more and more dependent on that. You can say that what is new here, people have been living all the past. So they were not, using or dependent on these societal applications of the ionospheric and thermospheric regions where these radiations are coming through, or the electromagnetic spectrum that we have been using so far have been, was not bothered. We were not bothered by what is happening up, but now we are more and more bothered, and we should be aware. Thank you all for your attention.
So we have some time for the questions. So yeah.
I just wanted to ask whether PRL or ISRO has any plans to take up operational space on the forecasting.
Yeah, definitely. There is first. This is what I showed you is one of the because for the forecasting you need to have real reliable data. So one of the things that I have that we have proposed and in the pipeline is to have space missions to get the data in a proper at a high density, high density, whatever parameters that we want actually to do that. But there is definitely, that is the whole ultimate goal actually.
The NOAA already has an operational space for the model, which create real-time predictions on a daily basis.
But then the thing is that they have different, kind of. We have to develop, within the country, this kind of strategic things actually. So it is important that we can't depend on external sources, and that too we can't. There are, of course, with this scientifically, a lot of work has gone in. There's some modeling is coming out, and we're also doing in other fashion. Still, prediction of BZ South is not known. What they do is based on data mining. Also, they use the data sets on that days of information to predict something, but we need to have more and more accurate predictions, and it's an evolving process. And then essentially, we as a country we need to have our own needs actually, because we can't depend on others in the long run.
Any other?
Well, beautiful talk. I really enjoyed.
Thank you.
This space weather, in fact, is more in the polar regions, right, compared to the lowland.
Yes, more on the highlighted, but they propagate. I didn't talk more on the science of it, because once these high latitudes, I told you that there is more heating that takes place because of the currents. There is temperature gradients that are created. So there are winds flowing from high to low latitudes. So low latitude also get affected because of the geomagnetic storm.
And you also showed that an anomaly Atlantic.
Yes.
That is where geomagnetic storms form.
Not geomagnetic, even irrespective of geomagnetic storm form. Geomagnetic storms, the effect is enhanced, but otherwise, because of the magnetic, field itself, there is a geodynamo. There is an anomaly in terms of magnetic field strength. That's why the B is varying there. There's a low B and low magnetic field, and there is a lot of particles coming in, and that region more. That is geodynamo. That is the way the Earth's core and that is rotating. That is completely. It's a given system to us. That's how it is.
Thanks, sir. Really enjoyed.
Thank you.
So, one question. Today we all hear about the sun. The space weather is all about sun, or any other entity we should
see. As I told you, the sun is the source, and poor fellows, we on the earth is the brunt, which is we in the sense ionosphere, thermosphere. So all the regions in between, sun definitely, because if there is no CME or coronal mass ejection happening, nothing happens here. So the source is the sun, but all the CMEs also don't come and hit the earth, because the magnetic fields have to be conducive for these particles to enter the earth actually. So there are, and also these have to be in the right direction. There are a lot of acceleration and deceleration processes going on between the sun and the earth because of the interplanetary magnetic field variations. So that also is an important thing which needs to be understood. So there are various elements, Sun, the interplanetary medium, the upper atmosphere, the magnetosphere, ionosphere, thermosphere, are all because in total we have to understand. Otherwise, we can have empirical kind of modeling. That also is possible. Different, but Sun is the source, and effects, cause and effect. That is the cause and effects are in the geospace.
Also, today all you talk about is electromagnetic particles. So, but there are other like meteorites. They are also space. Is it or is it not?
That doesn't come into the space weather domain. That's, of course, things are in the space. A lot of meteors falling every night. If you see, there are so few meteors you can see, and then there are different times. August or November, there are a lot of Leonite. Showers which are orientation, because a lot of bodies that are flowing around in the space. In terms of Kuiper belt between Mars and Jupiter, there is another source of these kind of meteors which are orbiting. And certain orientations, they come more and more. They come and fall, and then you can see more meteors. But they burn out in the upper atmosphere. Not even upper, even lower. At around 80 kilometers or so, the density is so large that they burn out. And sometimes they survive and fall on the ground, and that becomes a meteorite. And of course, PRL has a legacy of picking those meteorites and having a large number of studies of telling about the origin of that particular meteorite, and understanding, because as the meteorite is coming through in the space, it is recording what is happening in the solar environment or solar origins, and therefore it has that kind of information also. So in fact, we have just yesterday or not last month, we have the other meteorite which has fallen, and our scientists have come up with an article wherein the source of that and what the composition of it and things like that. So when it falls on the ground, it becomes in a matter of study, but that doesn't, unless it is a huge thing and falls on someone's head, there's no problem.
Okay, any other questions? Yeah.
Yeah, coronal mass ejection, again, it's a solar activity dependent. So if you have high solar activity time, there can be 2 or 3 in a day, and then low solar activity period, the number reduces. So it's again solar activity dependent. It has got 11-year cycle.
Any other questions by anybody? If not, let's thank the speakers. How? Any online questions?
Yes.
Can I see it or can you chat box? Okay. So in my MS Teams is the chat box. Your MS Teams. There is MS Teams. The form is open.
Yes.
Yeah. Yeah. Check the chat. Yeah. Can you read the question before you answer?
Yeah. See the chat. Okay, this is Professor Parthasarathi Mukhopadhyaya. He's saying, okay, interesting, informative. My question: do you envisage a Earth system model coupled with outer space to predict the space weather and climate? Yes, sir. That is the whole aim of our research, is to be able to come up with a clear, model which has both physics-based understanding and also be able to predict things accurately.
Okay, so we come to the conclusion of our today's colloquium. Thank Dr. Raju for giving a wonderful talk.
Thank you. Thank you very much. I'm sorry of this and disruption because of the movies.
Still, it went very okay. It was very nice and new topic for us.
Yeah, that's great. Off again and
ठीक है